Today we are going to mean and variance of beta distribution. What is the probability density function of a beta distribution? It is given as PDF function of x, so with the parameter alpha and beta equal to gamma alpha plus beta all over gamma alpha gamma beta, then x, which is the variable, raised to power of alpha minus 1 times 1 minus x raised to power of beta minus 1. So here the range of x is 0 to what? To infinity, or 0 to 1 rather. So we have 0 otherwise. So this is the PDF of a beta distribution. So now we want to look at the mean and variance of this beta distribution. Don't forget, we have treated the mean and variances of binomial distribution, Poisson distribution, and gamma distribution. So you can check the description box to find those videos. Now let's continue with this. So far, this is a continuous distribution with a random variable x. With this range 0 to 1, we can find the mean. If you recall that the mean of any continuous random variable is given as integral negative infinity to plus infinity of the variable x, then function of x with respect to the x. So this is the mean or the expected value of any continuous random variable x with the method of moment. Don't forget, we also have other methods which we can use, but we want to finish finding the means and the variance of all these distributions with the method of moment, and after that we go to other methods in order to know how they can also be derived. Our function of x is this, which is everything here. We insert this distribution here, and when we do that, we are going to have expected value of x equal to integral 0 to 1, that is the range of the variable, and we have an x. Function of x is this, which is gamma alpha plus beta all over gamma alpha and gamma beta, then x raised to power of alpha minus 1 into 1 minus x raised to power of beta minus 1 with respect to what? The x. So what you want to do now is you want to take out the constant term. That is, these parameters are the constant terms while x is the variable. We need to find the integral of the variable. So here we are going to have a gamma alpha plus beta all over gamma alpha times gamma beta integral 0 to 1, that's the range. So this is raised to power of 1, so this and this, if we apply the law of indices, we are going to have x raised to power of 1 plus alpha minus 1, then times 1 minus x raised to power of beta minus 1 with respect to the x, and this, we cancel this. We are going to have a gamma alpha plus beta all over gamma alpha times a gamma beta integral 0 to 1 of x raised to power of alpha into 1 minus x raised to power of beta minus 1 with respect to what? To the x. Here we want to apply the standard integral of beta distribution. We use this method when we derive the mean and variance of a gamma distribution as well. So we want to apply this gamma distribution from the standard integral. If you notice, if you recall that when you have a distribution from 0 to 1 as x of t raised to power of alpha into 1 minus t all raised to power of beta minus 1 with respect to dt. This is a standard integral proved to be gamma alpha plus 1 times gamma beta all over gamma alpha plus beta plus 1. So this is the standard integral. So if you also have, let's say we have let's call this number 1 and number 2, if you have another one like this, integral 0 to 1 of t alpha minus 1 into 1 minus t raised to power of beta minus 1 with respect to the t, and this will give us a gamma alpha then times gamma beta all over gamma alpha plus beta. The fact remains that we are adding, or we can use this logic as we are adding 1 to the power of the variable here. So that is why we have gamma alpha plus 1 for this rather, and this, when you add 1 to this, it will become beta. So that is why we have this. Then all over, or everything over the gamma of this plus this. So that is how we obtain this. Likewise this, if you add 1 to this, that is alpha minus 1 plus 1, we are going to have a ordinary alpha, and if you add 1 to this, we are going to add this, then addition of this into gamma. Therefore, you can now agree with me that from here we can have our expected value. It implies that expected value of x is now gamma alpha plus beta all over gamma alpha times gamma beta times, so this will give us, based on the theorem, it's like this, or we add 1 to this, it's going to be gamma alpha plus 1. Then when you add 1 to this times gamma beta all over this plus this, which should be gamma alpha plus beta, then plus 1. So that is the value. So now we want to reduce these parameters or these terms. Let's reduce this term. This can cancel this. This can take care of this. And also note that one of the rules or properties of this gamma distribution is if you have a gamma, let's say you have gamma n, if you have gamma n, this is the same thing as n minus 1 gamma n minus 1. It means we are subtracting 1. Here we are adding. If you are transforming it to the gamma function, we are adding 1. But if you want to remove it from gamma function, we are subtracting 1. That means if you want to further this is the same thing as you add 1 again. This can also be written as n minus 1 into n minus 2 gamma. So when you subtract 1 from this, it will be n minus 2. If you continue like that, it's just like a factorial. So when you are moving like n factorial, which is equal to n into n minus 1 into n minus 2 into n minus 3, like that, factorial. So that is the function we are using here. So we want to reduce these gammas in order to cancel this parameter. And if you do that, we are going to have our expected value of x equal to, so this is alpha. If we subtract 1 from this, it will be alpha plus a beta minus 1 gamma, or let's leave it so that we express this in a way that we cancel this directly. Let's just express this so that we cancel this directly. And to do that, we are going to have this remain as gamma alpha plus beta all over gamma alpha times, we subtract 1 from this, and when we subtract 1 from this, it's going to be alpha, then gamma alpha. That is, if you subtract 1 from this, you take it to the back, then you repeat the remaining function again, then all over this, everything here minus 1 will give us alpha plus beta, then this remain as gamma alpha plus beta. Therefore, this can cancel this can also cancel this. We have this, take care of this, we have this, take care of this, and our expected value of x will equal to alpha all over alpha plus beta. This is our mean of this beta distribution. This is the mean of the beta distribution. Then let's prove the variance of this beta distribution. To prove the variance, we note that the variance which is simply the variance of x is given x expected value of x squared minus expected value of x squared. So this is variance of any variable, either discrete or continuous distribution with moment method. So we are done with this. We know this already, which is the one we just proved here, and this is the value. It's our mean. But this, we need to find the value of this. Let's find this. Expected value of x squared is equal to integral the range 0 to 1 of x squared times our function of x with respect to the x. Our function of x is the distribution of the beta. So let's substitute this distribution to this function here, and if we do that, we are going to have a expected value of x squared equal to integral 0 to 1 the x squared here times this function, which is this gamma alpha plus beta all over gamma alpha times gamma beta, then times x raised to the power of alpha minus 1 into 1 minus x, then beta minus 1, all with respect to what? The x. So now, let's take this out, being the constant term. So we are going to have gamma alpha plus beta all over gamma alpha times gamma beta integral 0 to 1. So x times x here, when we take the common base, which is x, so the power will be 2 plus alpha minus 1 into 1 minus x raised to the power of beta minus 1 with respect to the x. This will give us gamma alpha plus beta all over gamma alpha times gamma beta integral 0 to 1. So this and this will give us x alpha plus 1 into 1 minus x beta minus 1 with respect to the x. We are going to apply those standard integral as well. So in terms of plus here, we can take or note that integral 0 to 1 of t alpha plus 1, like I said, we are adding 1 into 1 minus t all raised to the power of beta minus 1 with respect to the t will be equal to, when we add 1 to this into gamma function, is going to be gamma alpha plus 2. That's for this. And if you add 1 to this, negative will cancel. We have a gamma beta all over. We are adding this and this, so it's going to be gamma alpha plus beta, then plus 2. This plus this, we divide it by this into gamma function. So this can be written from here as expected value of x squared equal to gamma alpha plus beta all over gamma alpha times gamma beta, then this into gamma function will give us a gamma alpha, when we add 1, alpha plus 2 times this add 1 gamma beta all over this plus this in gamma form to be gamma alpha plus beta then plus 2. What you want to do now is we want to use this method to reduce this gamma function so that we'll be able to cancel those that are like terms in fractional term. So we can have this. We can have expected value of x here equal to, so I want to reduce this in order to cancel this. I will reduce this in order to cancel this, or this will go already, this will cancel this. So left with gamma alpha plus beta all over gamma alpha. Then this, if we subtract one from this, that is one from this, it will be alpha, plus 1. Then we repeat this again into alpha plus 1. That is, we subtract 1 from here to be alpha plus 1. So we take it to the back, we repeat the function again, all over. So this, I want to reduce it to this form, subtract 1 from this, it will be gamma, if you subtract 1 from this, we will get alpha plus beta plus 1. Then repeat it again, alpha plus beta plus 1. So let's take it one after the other. And we can still reduce this in order to suit this, and we can reduce this as well in order to suit this. And if we do that, we are going to have gamma alpha plus beta all over gamma alpha times alpha plus 1 times, so let's subtract 1 from this, we are going to have alpha, then we repeat it again, gamma alpha, so this can easily cancel this, all over alpha plus beta plus 1, add 1 to subtract 1 from this, we are going to have alpha plus beta, repeat this function again in gamma form, it's going to be alpha plus beta, which is gamma alpha plus beta. Now this can take care of this, this can take care of this, and we are going to have this cancel this, this cancel this, left it this and this, which is equal to alpha into alpha plus 1 all over alpha plus beta into alpha plus beta, then plus plus 1. This is our expected value of x here. Now, if this is our expected value of x here, don't forget we are interested to find the variance. We are done with this, and we've calculated this already, which is our mean, and that one is alpha all over alpha plus beta. We just substitute this, and we simplify. Let's see what we are going to have. If and only if all these are correct, we can now have our variance of x equal to this, which is expected value of x squared minus expected value of x all square, right? This will give us alpha into alpha plus 1 all over alpha plus beta into alpha plus beta plus 1 minus this, which is alpha over alpha plus beta. This is our mean arc square. So this, when you open this, it's going to be alpha square plus alpha all over. We can also open this if we like, and if we do that, or let's leave it first, it's going to be alpha plus beta all into alpha plus beta plus 1 minus this will be alpha square all over alpha plus beta into twice of this alpha plus beta. So now we can find the LCM of this. Let's find the LCM. So from that place, if you want to find the LCM will be alpha plus beta plus 1 and alpha plus beta square. We're going to have alpha plus beta plus 1 into alpha plus beta square. Now, this goes in alpha plus beta square. It should remain that. It simply means when we say this goes in this, what we are saying is that is alpha plus beta plus 1 into alpha plus beta all square divided by this, which is alpha plus beta into alpha plus beta plus 1. So that is what you mean by this goes in the LCM. That is the LCM divided by the first value at the denominator in the first fraction. We discover that this will cancel and 1 will cancel here, remainder 1. So this goes in this will just be one of this, which is alpha plus beta. So alpha plus beta. So we are using it to multiply what is here, which is alpha square plus alpha. Then minus, so this goes in the LCM here, means alpha plus beta plus 1 into alpha plus beta all square divided by that, which is alpha plus beta into alpha plus beta, so which is this, and to cancel this, simply this remain. So we can just say that alpha plus beta square direct remain that this. So we are taking this to multiply that fraction there. So it's going to be minus alpha square times this, which is alpha plus beta plus 1. Now we can expand this bracket and this to see if we can cancel. This time this will give you alpha cube. This time this will give us plus alpha square. So this time this will give us alpha square beta, and this time this will give us plus alpha beta. Then minus, this time this will give us alpha cube. This time this will give us minus alpha square beta, and this time this will give us minus alpha square all over. We can leave this like this as alpha plus a beta plus 1 into alpha plus a beta all square. So here we discover that this will take care of this, and this alpha square beta will take care of alpha square beta. Also, alpha square will take care of alpha square, left with alpha beta over this. Therefore, our variance will be equal to alpha beta all over alpha plus beta plus 1 into alpha plus beta all square. So this is the variance of beta distribution. Thank you very much. So if you are new here, please help me to subscribe. Click on the notification bell so that you get any video I upload any point of time. Please share, like, and comment. I love you all. Thanks.